Okay, let's start. Good morning. I'm going to take attendance today. So, forgot to close the door. Today we're going to keep working on metric spaces, continuity, and stuff like that. But before that, I wanted to say a couple words about problem sets. So by now, you have access to your grades for the first problem set. We were able to release them on Friday. And one of the problems was graded for accuracy. This relationship between a function being linear and its graph being a linear subspace. And if you go on Canvas, under the Pages tab, there is a now new item, Selected Solutions. And there, if you go and have a look at that tab, that item, you're going to see a PDF file where I wrote very explicit, very detailed solutions to that specific problem. I'm generally happy with the outcome. The average is around 8.5, 8.52, I think. So that's something we like. And I wanted to say a couple words, because in the feedback, some of you said things like, oh, I spent a lot of time and it's perhaps unreasonable and all that stuff. And so I want to give you some hints as to how you can optimize your time. And my idea is that if you know a little bit more about the design of this class and how things work, I think you can optimize it a little bit more. And so given any problem set, there's going to be probably 5 problems. 4 of the problems are going to be graded for completion, which basically means if you did something that seems relevant, you're going to get full credit for that problem. The remaining 1 problem is going to be graded for accuracy, which means that that you actually need to prove or disprove whatever statement you have. Now, I told you that which one of these 5 problems is going to be graded for accuracy is a mystery, right? So you don't know which one. But I hope if you know the design a little bit more, you might try guessing it. And so the idea is this, right? So one of the problems ultimately is going to turn out to be the one that is graded for accuracy. Then it's going to show up. So its complete solution is going to show up on Canvas. And I told you that because I'm emphasizing this particular problem, it is also much more likely for this problem to show up in the exam later. Okay? Almost verbatim, quite possibly. Maybe with some modifications. Maybe with some additional hypotheses so that the problem becomes easier. Now, exams, I don't like pushing students in exams that much. For instance, our midterm on Friday, it's a 50-minute exam, and you have only so much time. So that means that the types of questions that can show up on the exam are bounded in terms of the complexity. If that is the case, and if the problem for accuracy is preparing you for the exam, that means that probably, even though it is a mystery which one is going to be graded for accuracy, it's going to be the one that is perhaps the easiest or the shortest, right? Now, again, I'm not going to tell you this one is the shorter problem or it's an easier problem. Even to determine this problem is easier to solve than this other problem, even though you cannot solve them, it requires you to think a little bit about the content. And so I hope this is going to sort of help you out. So that means that when you're trying to when you're trying to complete the problem set, that means that a good strategy would be look at every single problem, let's say 15 minutes, 20 minutes, each and every single one. Then write, note down some sort of first ideas. Does anything pop out? Maybe examples, things like this. And then look back again. Which one is the easier one? I'll start with the easiest one, right? The one that seems easiest to you. I'm not saying this is going to work 100%, but I hope it'll help you out a little bit. Okay? Any questions about this? Now, another thing too, when you look at my written solution, so claim, proof, whatever, on Canvas, you're going to realize that I am being a lot more technical and explicit. So for instance, when I wrote the solution for function is linear if and only if its graph is linear, I use subscripts. Well, I guess initially I use subscripts for the addition, depending on in which space you're taking the addition. I become a lot more sort of explicit. And so this is also related to the following idea that, just like in regular communication, there's a difference between written language and spoken language. In math too, there's a difference when you're writing things. And of course, in these solutions, I'm trying to be a little bit more didactic as well. So I sort of try to give some idea and try to be as explicit as possible. So there's a difference. And hopefully in this class, you're going to develop both of these sort of modes of communication. When mathematicians are talking to each other, obviously they don't state everything explicitly. A lot of things are understood. And that's sort of the mode in which I teach in class. Whereas when I'm writing things down, I become more explicit, more technical, more detail-oriented, if you want. OK, that's all I wanted to say. Any other questions? Yes?
Which question on problem set 2 is graded for accuracy?
Oh, you're going to see it when it shows up. Yeah, hopefully for problem set 2, we're going to be able to release it on Wednesday. So you're not going to get the solutions, which means that you're not going to know which one is going to be graded for accuracy before the grades are released. OK? So we're hoping to release the grades and the solutions on Wednesday. Any other questions? OK. So here's this exercise. This is, I think, the third time I'm mentioning this. Part of it is because it is very likely that one of these things is going to be on the exam. OK? This is important. This is, so to speak, the limit laws in multivariable calculus. This is very important. Make sure that you can do these things. So we did something similar to this. Remember, on Friday last week, we showed that the d function, the metric on a metric space itself is a continuous function. There are a couple different versions. The moment you have versions of this, the moment you have a linear structure or a linear structure plus some additional things. So for instance, if I have a V inner product space, I can think of the inner product itself as a function from here to there. Right? It takes two vectors, gives me back a number. We said that any inner product induces a norm, and then any norm induces a metric, which means that, again, I can here look at the product metric. And if I have a function between two metric spaces, I can ask whether or not it is continuous. OK? And so I want you to really take these exercises seriously and write them down. Ultimately, even though I write these like this, so for instance, in order to show that this inner product is continuous, what you're going to do is you're going to take two sequences in V, both converging to two different possibly vectors, and then you're going to look at their inner products. So x sub n inner product against y sub n. Let's say x sub n converges to x infinity, y sub n converges to y infinity. Is it the case that their inner products or dot products converge to x infinity against y infinity? Okay. If I have, similarly, if I have a normed vector space, vector addition itself or scalar multiplication or norm, these are continuous functions. If I have three normed spaces, I can look at a sequence of linear transformations that are bounded linear transformations from V to W. Let's say that converge to something with respect to the operator norm. Another sequence of bounded operators from here to there, again converging. And of course, I can compose these two sequences. And the question is, if I were to compose an element from here to there and then an element from here to there, does the limit of the composition converge to the composition of the limits? Right? A special case of this is that if you have two sequences of matrices that you're multiplying, again, there should be continuity. Did you all sign this? Oh. Yeah. Okay. In short, linear algebra is continuous, okay? Whatever you do in linear algebra, most things are continuous. They're in fact differentiable, we're going to see, once we start talking about differentiability. Any questions about any part of these? Once you unpack all of these definitions, it's going to turn into take a sequence that converges, take another one, if necessary, sort of combine them in some way, and then try to bound the difference between a typical term and the limit term, right? That's what you do. Again, I'm repeating, and I'm not going to say this again, but in the first midterm on Friday, it's very likely that there's one of these is going to show up as a problem. OK. So we had talked about continuity in terms of convergent sequences being preserved. So we said, so if I have an x bullet, rather, x0 rather, and if I have a function from x to y, I have x0 here, f of x0 here. We said that this function is continuous at x0 if any input signal that converges to x0 transforms into some sequence in y that converges to f of x0, right? So something converges to this with respect to the metric on x. I don't know what it is, but it's something that has a triangular inequality, among other things. So this is, let's say, x1, x2, dot, dot, dot. I transform it, turns it to something like this. So this is f of x1, f of x2, and so on. The point is that maybe there are many different ways to converge to x0. It could be possible. Maybe something like this. Whenever an input signal converges to x0, I want the corresponding output signal to converge to f of x0. This was how we defined continuity at a point in terms of sequences. But there is a perhaps much more geometric way of thinking about this that doesn't use these signals. And that requires these epsilons and deltas. So maybe one of you can guess how I can characterize continuity at x0 in terms of epsilons and deltas. How do I characterize continuity at x0? You should have seen this in 3210. No? For any epsilon? Yes. Epsilons are always positive. There is a delta.
Such that absolute value x minus c.
X minus x0.
Okay, yeah.
Less than delta. But whenever we have this in single variable, right? This now we're going to think of it as the distance between x and x0. So once you do this change, everything works out. For any x and x, if the distance between x and x0 is delta at most, then the distance between f of x and f of x0 is at most epsilon. Okay. And so what is the picture that corresponds to this? Instead of now having signals, I'm going to have, in my mind's eye, concentric circles, or disks, let's say, that zero in to these 2 points x0 and f of x0. So again, I'm going to draw the picture. Some other set. Here is x0. Here is f of x0. For any epsilon, you start at the error margin you want to start with, you want to obtain ultimately. If I control my input to a delta, now I know x0 goes to f of x0, but I want nearby points to not cause a lot of error. So I'm bounding my error. Now that I have a bounded amount of error, I should have some limit as to how much I need to control my input to be within an epsilon. Within a delta, such that any point within delta of x0, let's say here, gets mapped to some point within epsilon of f of x0. Okay. This is the idea. So depending on the situation, sometimes using sequences is easier. Sometimes using the epsilon delta is easier. Okay, that depends on the context. Epsilon delta is a little bit more geometric, perhaps. In fact, what you can say is that, well, think of the set of all those x's that are within a delta of x0. That, what we're going to call, is an open ball centered at x0 of radius delta. We're going to spend time on this terminology later, but I drew here the ball, okay? This is the delta ball centered at x0. Maybe I should say open delta ball. At x0. And of course, this red disk is the open epsilon ball centered at f of x0. And so and what I want for continuity is for any epsilon, I want to be able to find, let me draw this again. It's epsilon ball. That's the delta ball. Center at x0, center at f of x0. Okay. This statement is equivalent to this. For any epsilon, there's a delta such that if I were to take this delta ball and apply f to it, the image of this ball under f is going to be completely within this epsilon ball. Maybe now it's not going to be a ball anymore. Maybe it's like a weird blob. Maybe it's something like this. Okay, but it's completely within the epsilon ball. So this is the image of the delta ball under F. Okay? Any questions about this equivalence? Of course, we need to prove it. And this is the intuition. By the way, if you want more sort of heuristics and stuff like that, when I taught the 3210, I defined pretty much all of these in the context of metric spaces, and there too, I discussed the heuristics. So you might find it useful to go back and have a look at those explanations again. Anyway, so we need to prove this. It's an equivalence, right? If and only if, which means that we need to prove two statements. Let's start with the backwards direction. Let's assume the epsilon delta statement and show that for any sequence that converges to x0, its image converges to f of x0 under f. Proof. Let x bullet converge to x0. Right, that was my notation. In terms of limits, if you want to open this up, I would write it like so. Limit as n goes to infinity of d of xn and x0. So the distance between the nth term x sub n and the target point x sub 0. I want this limit, it's the limit of numbers. I want it to go to, I'm assuming that it goes to 0. What I need to show that f of x bullet converges to f of x0. Again, opening this up, now that this is a signal in y, I need to basically look at the same statement, except that the metric is going to be the metric on the output space y. That's what I'm trying to prove. Okay, how to prove that a sequence of real numbers converges to 0? Converges to 0? Well, you open it up, you say for any epsilon there's a capital N such that for any lowercase n after capital N, this number is within an epsilon of this guy. So let epsilon be positive. Okay. Now we assumed this epsilon delta statement, right? I'm going backwards. There is some delta such that for any x and x, this happens. If x is within delta of x0, I know that f of x is within epsilon of f of x0. What is the next step? I use the only hypothesis I have. What to do now? I was tricking you because I assumed one more thing, right? We assume that we have a convergent sequence. But if x bullet converges to x0, that is to say, if this sequence of real numbers converge to 0, then after finite time, this number is going to be less than delta. Yes? There is an n, so maybe I should say, here's a red star. By the red star, there is an n such that for any lowercase n after n, so I waited n times, capital N times, and after that time, I know that my signal is going to be within delta of x0. Well, x sub n is a term, is a point in capital X. If x sub n is within delta of x0, I can apply this implication. By the green star, or maybe you should use a different color in case color blindness, something like this. By this other symbol, box, there's an n such that after that, dy of f of x sub n, so I need to be applying f to this, comma f of x0 is within delta. Which was what we were trying to show. For any epsilon, I found sometimes such that after that, this term is within epsilon. That's the definition of this limit. Yes?
Is it the same n?
Yes. Yes, it's the same n. Yes. Yes. Any questions about this? Okay, so now we need to do it the other way around. Let's remember our logic. So last semester when I taught the first part of this class, 3210, I went over logical symbols and proof methods and all that stuff. But in case when you took this, they didn't discuss this stuff, here's some logic. Okay. So this statement we have is of this form. P is one statement, Q is another statement. We're showing if and only if. Of course, this is equivalent to P implies Q and Q implies P. And so we can say this is logically equivalent to P implies Q and Q implies P. Now, so far, we showed this part. Okay, we assumed Q, we showed P. So we need to show this part. If f is continuous at x0, continuity in this in the sense of sequences, then the epsilon delta statement holds too. That's what we're trying to show. Now, one of the methods of proving statements of the form P implies Q, it turns out, is to instead show not Q implies not P. This is what is called proof by contrapositive. So to show P implies Q, you say, let's say the conclusion is not satisfied. Then you show the only way this can happen is if the hypotheses are broken. So this is my notation for not. Not Q implies not P. As you can see, there's also some sort of algebra that governs logic, at least this type of logic. There are different logics, apparently. But this is the logic that we're using, at least in this class. And because of this algebraic nature of logic, too, computers actually work. Right? So ultimately, these are, you can basically sort of physically represent them using electrical circuits if you want. These are AND gates and OR gates and NOT gates and stuff. We're not going to use them, of course, but good to know. And so this is what I'm going to do. To show this implies this, I'm going to assume not this. I'm going to assume that the epsilon delta statement fails. And I'm going to show that f cannot be continuous at x0. Any questions about this stuff? Okay. So, again, if you want sort of like a more detailed account of this, have a look at my 30-10 lectures. Say the opposite of this guy. So what I'm going to do is I'm going to write the statement, and I'm going to negate it. Okay? Let's do this once. Going forward, I'm not going to keep writing this. For any epsilon, there's a delta, such that for any x, if x is within a delta of x0, then f of x is within epsilon of f of x0. So this is the statement I'm trying to negate. I'm assuming that the conclusion fails, not this. It turns out that there's a rather straightforward way of negating statements like this, especially when you write them in this form, where you have first quantifiers and then the statements. You keep the orders, and then you flip the quantifiers. For O's turn into there exists. There exists turn into for O's. And implication turns into something, which I'll tell you. This is equivalent to saying that there's an epsilon, such that for any delta, there is an x, such that. So the only way this can happen is that this holds, but not this. That is to say, this x in x is such that it is within delta of x0, but its image, f of x is not within epsilon of f of x0. That is to say, the distance between f of x and f of x0 is not less than epsilon, but greater than or equal to epsilon. I'm assuming this. Okay? And people typically decorate the stuff, especially when you have one epsilon that you're going to use. Let's say epsilon 0. For any delta, I'm assuming that there is some point within delta of x0 whose image is farther away than f of x0. That's what I'm assuming, essentially. I just cannot approach f of x0 using these specific points. OK? So from this statement, what I'm going to do is I'm going to basically farm a sequence. Farm a sequence that converges to x0, whose image stays away from f of x0, which is going to give me a contradiction for continuity. Let me delete this part. So how do you farm a sequence like this, from a statement like this? Well, you take a sequence of deltas that decreases to 0. For instance, I can take delta to be 1, 1 over 2, 1 over 3, whatever. There is an x1 in x such that d of x1, x0 is bounded by 1, but d of f of x and of x0, I stopped writing the subscripts at this point because it becomes pedantic. Then I use, for instance, delta equals 1/2. Again, this statement tells me there's some other points. Maybe it's the same point, but I don't mind. It's still going to create a sequence for me. x2, x0 is within 1 over 2, but d of that was 1, f of x2 and f of x0 is bounded from below by epsilon 0. You keep going like this. By the principle of mathematical induction, this gives you a well-defined sequence in x that converges to x0. You never write this, by the way. We're using induction here, whatever, in regular sort of speech. I'm just doing it once for once. Mathematical induction. X bullet converges to x0, but f of x bullet does not converge to f of x0. That is to say, f cannot be continuous. And that's the end. Okay. Questions? Comments? Okay. So next up, let's delete this. Well, the composition of two functions that are continuous itself is continuous. Lemma. Let x, y, z be metric spaces and let f and g be continuous functions, f from x to y, g from y to z, so that I have g composed with f. Then g composed with f from x to z is continuous also. If you want to write this in short, you can just write, if f and g are in C0, C0 was the space of continuous functions, or set at this point, set of continuous functions, then g composed with f2 is continuous. Using sequences, for instance, here is a lot more convenient than the epsilon delta. I'm going to leave the epsilon delta proof of this to you. I'm just going to use sequences. So I'm going to take a convergence sequence in x, apply g composed with f to it, and I want the outcome sequence to converge to the corresponding limit. Proof. Of course, this is a sequence in x that converges to some point in x. By the continuity of f, so f is in C0, which means that the image of this sequence converges to f of x. G is in C0. It's a continuous function, which means the image of this particular guy in y converges to the image of this. But of course, this is the definition of g composed with f being continuous. See? very pleasant. Now, it's still a good exercise to verify the same statement using epsilons and deltas. You're going to have to sort of do this epsilon delta shenanigans a little bit. Show the same. Using epsilon delta. Okay. Comments? Remember on Friday I told you we have a bunch of different structures, and whenever you have a metric, you have what is called the topology. I didn't define the topology, and we're not going to define it in this class. But some of you are interested in this more advanced class that focuses on topological spaces. The main difference between metric spaces and more abstract topological spaces is that somehow in topological spaces, you can still talk about convergence and continuity, but you don't get to use sequences somehow. It's more complicated. So in a sense, sequences are your friend. Makes a lot of things easier, in my opinion, at least once you get used to them. And so let's now discuss some of the structures defined by metrics. So in single variable, right? So if x is r, the reals, of course the absolute value of the difference of two numbers is a metric. So it's a metric space. And we have a very convenient theorem that is more advanced than the standard limit theorems. Namely, we have what is called the Bolzano-Weierstrass theorem. What does that say? What does BW say for reals?
Is it for every bounded sequence there is a convergent subsequence?
Yeah, so basically we want to do the same thing. For arbitrary metric spaces, that's going to fail, it turns out. But at the very least, we should be able to do the same thing for Rn, right? So we need to talk about what it means for a sequence to be bounded. We need to discuss what it means to take a subsequence. We know what it means to converge. Okay, so we have a bunch of things to define. Let X be a metric space. For A, a subset of X, I'm going to define the diameter of A to be the extended number that is the sup of distances between any 2 points in A. Diameter of A is diam of A, which is a sup of D, let's say A1, A2, where A1 and A2 vary in A. Instead of writing sort of like a set, you can just write the variables underneath the sup as well. For brevity, in principle, this could be an extended number. So it is possibly infinity. It's the diameter. In a sense, this too is continuous, but we're not going to develop the structure to make sense of that statement. So we're not going to. So at the very least, we have a number or extended number associated to any subset. So the diameter of the reals is infinity, of course, right? But the diameter of, let's say, the closed interval from 0 to 1 is going to be 1. I'm going to call A a subset bounded if its diameter is finite. finite. If I have a function between metric spaces, I'm going to call it bounded if its image is bounded as a subset. If S is a set and F goes from S to X, it's a function, F is bounded if its image, if f of capital S, the image set, which is f of S, where S varies in S, is bounded. Let's say f sub b, lowercase b, S to X is going to be the collection of all bounded functions from S to X. So the collection, or the set, and finally, if S2 is a metric space, I can talk about continuous functions, which means that I can talk about functions that are both continuous and bounded. That I'm going to denote by C0b. Maybe let's do this. C0b x y is C0 xy, that's the collection of all continuous functions from x to y, inter fb. Intersection from x to y. Warning, this bounded is not the same bounded as the bounded that we discussed before. Bounded linear operator doesn't mean bounded in this sense. I made the same warning when I defined the other bounded, but just reiterating. So this is bounded in the sense of metric spaces. It's an unfortunate situation that we have same thing used for two different ideas. Okay, I think I'm out of time, so this will be it for today. I'll see you tomorrow. Where's the attendance sheet? Okay, let's start. Good morning. So we're on our way to state and then prove Bolzano-Weierstrass for at least RD, d-dimensional Euclidean space. Yesterday we had defined notions around diameter and boundedness and stuff in the context of metric spaces. And I also mentioned these open balls. And today I want to start with introducing some syntax around these open balls, closed balls, and so on. Compare, perhaps, or relate boundedness of a linear operator to the metric space world. And then we'll focus more on Bolzano-Weierstrass. Are there any questions before I start? Okay. So this is a very common idea open balls, closed balls, and spheres in metric spaces. Although the notation I'm introducing here is somewhat idiosyncratic. In a second, I'll tell you why this is a good notation, at least in my opinion. And I'll give you some alternative notations as well. And so this is all about this, right? So if you have a metric space x, comma d, so x is a set and d is a metric. So d is your fundamental function. And so one of the things you can do when you have a function is to look at its level sets. So subsets where the function is constant, or you can look at sublevel sets. And so what you typically do is, because d, the metric, takes 2 inputs, you fix one of them, and you let the other variable as free. And then you look at these things. And so xd, and then this is the bracket notation, I'm defining this to be this set. That is to say, it's a set of all those x's whose distance from x0 is less than or equal to r. So this is called the closed ball, centered at x0 with radius r. If instead of having less than or equal to here, if I have less than, same thing, right? So all those points whose distance from x0 is strictly less than r, that's called the open ball. And if the distance between x and x0 is exactly r, that is called the sphere. Okay? So the common notations for these type of things, so for instance, for this one, you'll see things like this. So I think in the textbook, they write it like so. B sub r of x0. The reason why I don't like this notation is that I don't like to bound the letter b to a ubiquitous object as ubiquitous an object as a ball. Because b maybe is a matrix and blah, blah, blah. And we have in this class a bunch of different structures that are sort of interrelated. I'd rather leave b as a variable. That's why I don't like using the letter b. In other context, you might see b of x0 comma r, or maybe it's the other way around, or maybe it is u x0 r, and so on. There's a bunch of them. So there is no common notation for open balls, closed balls, and stuff. And spheres too, maybe you might see something like this, s sub r of x0. There's a bunch of notations. But I'm going to consistently use this bracket notation. OK, so let's look at some examples. I should mention one thing. If the context is clear, that is to say, if the ambient space is clear, I'm going to drop this, and I'm just going to write this bracket. So for instance, if x were, well, R3, let's say, this standard metric, Euclidean metric. Let's say x0 is the origin. And let's say that r is 1. Okay, so what does this mean? So x0, let's say, less than or equal to r, close bracket. Okay, this is the 3-dimensional ball of radius 1 centered at the origin. And so this is triples xyz such that the distance between this and this is bounded from above by 1. And so what is the distance between this and this? X squared plus y squared plus z squared in square root. I want this to be less than 1. Okay, x, y, z. This is, so this is 1, this is 1, this is 1. Everything inside is included in this set. Okay, so in the standard setting, it coincides, the closed ball coincides with what you know from calculus. But for instance, I can do this too. Let's say we're on the plane. Of course, if I were to do the same thing, now I would get the so-called two-dimensional ball, which is not really a ball in the sense of, let's say, physics. It's not a three-dimensional thing, but it's going to be a disk. Okay? Of course, in one dimension, it's just going to be an interval. But for instance, what I can do is, instead of using this L2 metric, I can use the L1 metric. Let me remind you, instead of looking at the squares, you look at the first powers of the components. And so here, d of x, y, and x bar, y bar is x minus x bar in absolute value plus y minus y bar in absolute value. This metric is induced by a norm. We didn't prove it, but this L1 norm is a norm that you can assume for the midterm. And so it's a metric. But when you think about it, what is, for instance, the unit open ball? Let's say my x0 is, again, 0, 0. For a change, maybe we can do 1, 0, actually. And let's say r is 1. And let's say that I'm trying to find the open ball centered at this point of radius 1. So that I would write like this. So R2 with respect to L1 metric, okay, 1, 0 is the center, and then open ball of radius 1. Okay. Now I want to draw this set. It's a subset of the plane. Its center is, so the center is always included in an open ball. That's the center, 1, 0. So for instance, if I were to look at 2, 0, the distance between 1, 0 and 2, 0, when you compute this, is again 1. That means that I cannot quite include 2, 0, but anything in between should be included. And likewise, the 0 vector, 2, is exactly of distance 1 from 1, 0. And likewise here, for instance, if I have 1 here and then minus 1 here, like this. But you're going to notice that if you were to try to sort of keep computing a bunch of different points, you're going to see this diamond shape. So the boundary is not included, but everything in between is included. Okay? So this idea that a ball is really sort of like this round thing is not part of the definition. Because this is an abstract thing, you're just defining things in terms of this idea that, oh, a sphere, for instance, is, okay, so it has to have a center, and a sphere should consist of all those points that are equidistant from that center. Whatever your metric requires that to look like, that's how it's going to look like. It's not actually going to look like necessarily a sphere that you're accustomed with. Okay? Okay, here's another example. So for instance, what I can do is, let me get rid of this part. Let's say we're in the plane, but instead of looking at the whole plane, let's take the unit square, so to speak. X is 0, 1 times 0, 1 inside R2. So I'm thinking of this as a metric subspace. And the metric I'm going to use is a standard metric. And again, I want to think of x, let's say at the origin. So 0, 0 is included here. Of radius, let's say 1/2. Open. Let's see, open. What is this? So you see, according to the syntax, here I'm including points only in x, only in this square. So what's going to happen is this. Okay, this is my x, this whole square. The center of the ball is the origin, so the bottom left corner. Radius is supposed to be 1/2. So the boundary is not included. Maybe I should draw it like so. Not included, but everything else that are closer, as close as is. Okay. So somehow this open ball looks like this, even though I'm using the standard metric. Okay. Questions?
So, would it be possible to do a weird, screwed up version of trigonometry with this? Or does that require more structure in our set?
I mean, I guess it requires, or it depends on how messed up of a trigonometry you allow, right?
I suppose that's fair enough.
Yes. Yeah. Yeah.
Could you explain one more time how the DL1 metric is different from the standard metric?
Sure. So, for instance, let me just compute the distance between 2 points. It's easier, I think. So, for instance, let's look at this. L1 on R2. So in a sense, you see L1 is easier to compute than L2 because you're not taking the squares. But also, absolute values, when you look at this, is not differentiable in a sense. So you're losing differentiability. That's why when people look at optimization and stuff, you would look at least squares. It's more common. Instead of, you can try optimizing this too, which people do, of course. But things have places. So let's say that, let's try to find the L1 distance between 0, 0 and, well, 1/2, 1/2. One half, 1/2. So the Euclidean distance between the origin and 1/2, 1/2 is what? So it is √2 times one of these lengths, √2/2. Okay, so the L2 distance, so if this were a 2 here, this would give me √2/2. Here, though, all I need to do, so it's going to be different, as you see. This minus this is 1/2, plus this minus this is 1/2. So the distance is 1. Okay. So somehow, you see, depending on this exponent p, remember this LP, L2, or L infinity, these are all sort of part of this family of metrics. What ends up happening is that somehow, as you vary p, you sort of change the shape of the balls. That's what happens. Maybe I should mention a couple more words about this. Say a couple more words. Just to remind you, I defined this before, but I didn't show that they were norms. So I'm just looking at points on the plane. R2 is a vector space, and I can just look at the LP norm on it. And so this is going to be x minus x bar in absolute value raised to the power p plus y minus y bar in absolute value raised to the power p. Everything raised to the power 1 over p. If p were 1, of course, I don't have this 1 over p. I just have absolute value here. And if I have p equals infinity, I really mean the limit. And in the limit, this just becomes the max. Maybe I should write that as well. You look at the absolute value of the difference of the first components, put that aside. Then look at the absolute value of the difference of the second component, put it aside, and look at the max of these. That's the infinity metric, L infinity metric. And so what happens is, as you change p from 1 to infinity, so you start at a diamond with a graphing calculator. If you can do animations, you can easily show this actually. Maybe you can use Desmos if you want. What happens is this. So for instance, 1, 0 is always going to be 1 distant from the origin. Okay? So these points are stationary. If p equals 1, or maybe I should start with the p equals 2 case. P equals 2 case is the perfect square circle case. Okay? This is the one that you know. P equals 1 case becomes this diamond. Maybe I should ask you, how does the L infinity ball look like? So for instance, 1, 1 is, so this would be 1, then this would be 1 if the other point were the origin. So somehow in L infinity, 1, 1 is 1 distant from the origin. It's kind of bizarre. So the L infinity ball is a square actually. So as you're raising p from 1 to infinity, what happens is you start with this diamond, and as you're raising a p, sort of gets more and more bulbous. As p becomes equal to 2, it becomes this exact circle. If you keep increasing p, it becomes sort of like, it gets closer and closer to this rectangle, and in the limit, it becomes an actual square. Okay? This is the sort of idea. And depending on the context, of course, why are we interested in these kind of things? For instance, at the very least, for application purposes, so these metrics often are used to minimize them. So you have sort of like a space, and you have one of these metrics, and somehow, for some values of p, optimization works better. Which p? That depends on the experiments and whatever. Okay, that's not part of abstract math. Somehow, different p values correspond to different energies, senses of energy. In probability, you call these different moments. Okay. Very, very important. In sort of like pure math circles, we don't really emphasize these different p's. They're all pretty much the same, at least for finite dimensions. But still, they're very nice to be aware of. Okay? Any questions about this? Many of you are applied math majors, and That's part of the reason why I'm sort of including some things that are more application oriented, even though they kind of make the math a little bit more complicated. Okay, so that's that. So going forward, I'm going to keep using this notation. And like I said, often I'm just going to drop this part, just going to write this bracket. You're going to see it's very convenient. Okay, so here's an exercise. We defined what it means for a subset of a metric space to be bounded last time. We said that bounded, a subset is bounded if its diameter is finite. In fact, you can also say this. Let X be a metric space and A be a subset. Then A is bounded if and only if it is included in some closed ball. If and only if, so how can I write this? There is some x0 and some r such that, well, A is included in the R ball centered at x0. And in fact, what you can do is, if X happens to be a normed space, so that the metric is coming from a norm, you can say that a subset of a normed space is bounded if and only if it is included in a ball centered at the origin. So you can choose this x0 to be the origin. Norm space S, a subset of V, is bounded if and only if there's an R such that S is included in the R ball centered at the origin. And of course, these definitions trickle down to functions, sequences, whatever. And this is often the definition we use in 3210, for instance. We say a function is bounded if its absolute value is bounded by some number for any input value. You're using the fact that R reals itself is a normed space. OK. Let's now connect boundedness of operators to metric spaces. Now, I told you a bounded linear operator is not the same thing as a bounded function, even though I can think of a normed space as a metric space. But somehow, boundedness of the operator relates to a different property that is available in the context of metric spaces, that is continuity. In other words, it turns out that the linear transformation is bounded if and only if it is continuous. This is a very important statement. So let's prove it as well. Lemma be normed spaces, and let's let A to be a linear transformation, possibly unbounded, from V to W. And A be linear. Then the following are equivalents, which I'm going to abbreviate as TFAE. Just to emphasize, the operator norm of A is bounded. This is a bounded linear operator. A is a continuous function relative to the metrics induced. A is in C0. Recall that this was my notation for the collection of continuous functions from here to there. And in fact, this also turns out to be equivalent to saying that A is, let's say, continuous at the origin. There are many more statements that are equivalent. I'm not going to state them. That's why instead of bounded linear operator, you can also see the phrase continuous linear operator. They are the same. When I was first learning this stuff, after seeing this, I remember thinking to myself, well, if boundedness for operators is the same thing as continuity, why not just define continuous linear operators? Because boundedness is like, forget about the notion of boundedness, because boundedness also means something else, right? There's a collision in the meaning. But now that I'm teaching, I realize that the point is perhaps that once you have linear algebra and infimum and supremum and stuff, we can immediately define what it means for a linear transformation to be bounded. But for continuity, you need to develop a lot more stuff. That's, I think, my idea. That's the reason. So let's prove it. Of course, 2 implies 3, because if a function is continuous, it is continuous everywhere. So we need to go from 1 to 2, and then from 3 to 1. We can use epsilon delta, like we discussed yesterday. Let me use a sequence. I like sequences more. Let's say let V bullet converge to V infinity, be a convergent sequence in V. What do I want? I want the outputs to converge also. A V bullet, I want to converge A V infinity. What does this mean? OK, I want the distances between an arbitrary term here and this to go to 0. This is a distance in W in the output space. But this distance, d sub W, is not some random distance. It's a distance that is compatible with the linear structure, and in particular with the norm. And in that case, this distance is nothing but the norm of the difference of these two vectors. So we need to show that this norm goes to 0. But of course, this, because A is a linear transformation, I can combine these. OK. So there's a parenthesis here. Oops, sorry. But then by the definition of the operator norm, I can split this, right? I can say that this is upper bounded by the operator norm of A times the norm of Vn minus V infinity. What is the final step? I have all this. I'm trying to show this goes to 0 as n goes to infinity. And I upper bounded it by this. There's a final step.
0.
Right? So this guy, Vn converging to V infinity, is the same thing as saying that this number goes to 0. This is a finite number. Finite number times something that goes to 0 goes to 0. Okay? So I have convergence. Does this make sense? Questions? If this is not clear, you should ask now. It's going to get more complicated later. Okay? Okay, so we showed 1 implies 2. 2, of course, implies 3 because continuity, literally by definition, is saying that it is continuous at any point. In particular, it is continuous at 0. So now we need to show that if I have a linear transformation A that is continuous at the origin, at the 0 vector, then in fact its operator norm is bounded. Let me write it like this, perhaps. 2 implies 3 is, by definition, of continuity 3 implies 1. How to do this? Well, now perhaps it's easier to use the epsilon delta. For any epsilon, there's a delta such that for any v whose norm is bounded by delta, AV has norm bounded by epsilon. Like that was the epsilon delta definition. So we have that for any epsilon, there's a delta such that for any v in V, if the distance between V and 0, that is to say if the norm of V, is bounded by delta, then the distance between AV and A0, that is to say the norm of AV, if you want, is bounded by epsilon. We have this. In particular, let's say for epsilon equals 1, I have some delta for which this works. Okay. Now I'm trying to bound AV in norm for an arbitrary input. Let me say, and let delta be the corresponding, be as above. Okay. What do I want? I want to show that the operator norm of A is bounded. In other words, I need at least one number, some alpha, such that for any B in V, AV in norm is bounded by alpha times V in norm. Once I have such an alpha, then I can optimize over all possible alphas, and that is the definition of the operator norm. I don't need to compute what the exact number this is. I just need to show that it's a finite number. Okay. Now certainly, this equation, or this inequality rather, holds for V equals 0 no matter what alpha is. So V equals 0 is not the problem. Let me assume that V is not 0. It's an arbitrary vector. Now here's what I'm going to do. I'm going to try to rescale V in such a way that I can apply this statement. And here's the idea. Let me draw the picture. This is perhaps an infinite dimensional space, of course, but the idea is going to work still. Let's say here's V. Okay? And this is the unit sphere. These are all vectors that are of norm 1. Now, if I were to scale V by 1 over V norm, I would get this particular point. Okay? I'm just shrinking V to the unit sphere. I scaled this so that now this new vector has norm 1. Okay? Now, if I were to multiply that, rescale that vector, again by, let's say, delta over 2, then I can apply this implication. Let's say V tilde defined by delta over 2 times V divided by V norm. Okay? The norm of this vector is delta over 2. Which is less than delta. Because of this, I can apply this and say that A V tilde in norm is bounded by epsilon. Hence, by the red star, oh, and epsilon is 1, of course. We chose epsilon to be 1. Okay, but what is this? What is A V tilde? Remember, V tilde is nothing but a scalar multiple of V. And because A is a linear transformation, I can take the scalars out. So this is delta divided by 2 times 1 over V norm. This is a positive number, which means I can take it outside the norm as well by one of these axioms, times A V. Okay? It's less than 1. Take this stuff to the other side. Gives you this, which is what I wanted. If you want, you can sort of like increase this. Should be 2 over delta. Let's say it is less than or equal to 3 over delta if you want. Doesn't matter. The point is that I was able to come up with an alpha that works for any V whatsoever. Okay, and that's the end. So 3 over delta, where delta is the delta that works for epsilon equals 1, is a possible choice for alpha. In particular, in fact, what this says is that the operator norm of A is bounded from above by 3 over delta. Of course, maybe, quite possibly, this is a bad bound, right? Because delta heuristically is a small number, which means 1 over delta is a very large number. So it's not a good bound, but it's a bound. It's a finite number. Are you happy with this?
Well, the 3 over delta, since it's going to be a huge number, but
Yes, yes. I mean,
the idea is you choose it for any, but I guess any.
yes. Yeah. We're not saying anything about how nice this is. You see, this is why continuity is not really. I don't consider continuity or metric spaces and stuff to be part of calculus because it's very flexible. You can just stretch everything and it doesn't matter. Bounded operator. There's bounded and there's bounded. I want my bounds to be very small if possible. Yeah.
How did the proof we did on the 3 or 4, that first proof from point 1 to 2?
Yes.
How did, I followed the math we did, but how does that show the one statement implies the other? Does that make any sense?
Okay, I fast forwarded this, but I said if I want to show that A is continuous, that means that it is continuous everywhere. Let's let B infinity to be an arbitrary point. In order to show that A is continuous at B infinity, I would need to show that for any sequence that converges to this B infinity, the outputs converge also.
Okay, and then the idea is you show that at every point, and therefore it's
Yeah.
Okay.
Yeah. I just didn't write that part. Yeah.
Why do you change it to 3 over delta?
Because technically here, this is less than or equal to. I mean, why did I choose delta over 2?
Yeah.
Doesn't matter. It was some number that was less than delta. Yeah. Yeah, you see, it's like when it comes to inequalities, there are two things. One is if for some number, for some alpha, this holds, but then once you have something like this, you can ask, is this a strict inequality? Or what are the best bounds? Operator norm is actually that, right? Like you're sort of trying to quantify it even further. An interesting thing, for instance, is that, for instance, in finite dimensions, if you were to think of a square matrix, n by n matrix, as a linear transformation from Rn to Rn, but let's say in the input, you use the LP metric, or norm, and in the output, you use the LQ metric for possibly different P and Q. It turns out that, for instance, if P is infinity and Q is 1, computing the operator norm of such a matrix turns out to be NP hard, if you know what that means. It means it takes a lot of time. It's not a good thing to do. It exists, it turns out. It always is a finite number. But, people, especially in computer science, they really need specific numbers for these kind of things. So. Okay. So it's interesting, you see. Boundedness in the sense of linear operators really is continuity, okay, in terms of metric spaces. Okay. Did this, that. Okay, let me define subsequences. You, of course, know subsequences from 3210. But how does one use subsequences using the bullet notation? And this is really the benefit of the bullet notation, is sort of saying things like x sub n sub k sub l sub I. You just use what I'm going to describe now. So let's say first a strictly increasing function j defined on the non-negative integers, my time variable, so to speak, is a function so it's an arithmetic function if you want, takes an input, takes an integer as an input, gives back another integer, such that if for any n, if I were to compare j of n and j of n plus 1, well, this has to be strictly greater than the other one. So as time goes to positive infinity, j of n increases, strictly increases. If this is the case, then we're going to say that for x a set and x bullet a sequence in x, let's write it like this explicitly. So it's a function from non-negative integers to x is a sequence. A subsequence of x bullet is, let me continue there, is a sequence let's say x bar bullet such that x bullet bar or x bar bullet is the composition of the original sequence by some strictly increasing function j. Standard example, of course. X sub n, let's say, is -1 to the n. So this is an oscillating sequence. I'm sure you're familiar with this. If j of n is 2n, so if I'm doing double time, I'm getting rid of either minus or plus. Right? X sub 2n is just 1. Composed with j of n is just the sequence that is constantly 1. So you're getting rid of the part of the signal that is dipping down underneath the x-axis by doing double time. This is like a time fast forward, if you want. That's how I'm imagining it. OK, I think that's a good place to stop. So we're done with the material for the first midterm. Tomorrow, we're going to have review. No recording will be made. And please come with your own questions. Thank you.